experiments one can do. So I'm going to tell you today about what we have done. This picture this looks like Apollo 11 landing, but this picture just illustrates one of the kind of questions here. You could make a Rydberg orbit with the electron distribution trailing behind as it comes down, or as I showed in the first one, coming towards, and ask questions about how that, whether you have a surface-oriented or a vacuum-oriented Rydberg wave function, how that affects the basic process. And these are actually real calculations for a hydrogen atom. And as you saw there, I'll just run that once more. For a hydrogen atom, one predicts that obviously if the Rydberg wave function is pointing towards the surface, it ionizes much more easily than if it's pointing away. But for other atoms and molecules, that may not be the case. Okay, so I'm going to talk actually about our experiments we've done with H2 Rydberg molecules at a variety of surfaces, both metal surfaces and surfaces with thin films. And I'll be showing some wave packet calculations that we've done to explore various other aspects of this process. These are the people who've done the work, particularly Eric So and Martin Bell, who are responsible for the calculations, and Ellen and Mark Ford, particularly most recently for the experiments. Okay, so thinking about the basic image charge effect when a Rydberg state interacts with a metallic surface, then one can think of this as the interaction between an ion and its image charge, the Rydberg electron and its image charge, and of course those are both attractive interactions, and then you have a repulsive interaction between the Rydberg electron and the ion image charge, and likewise between the electron image and the ion, and this all sums up a very long range to a basic van der Waals force. At shorter range, however, then these, according to which state you're actually populating, then different terms in this may actually dominate. This shows you calculations from Peter Nordlander for a hydrogen atom approaching a surface. This is at 600 Bohr radii, for n is 9 and 10. And you can see the splitting of the energy levels here as you approach the surface. And basically, we're getting a kind of Stark effect. And the states which are going up in energy, in fact, we've taken away the attractive ion image interaction from this picture. The states which are higher in energy are ones with the Rydberg electron pointing away from the surface. The ones which are lower in energy are with the Rydberg electron pointing towards the surface. I guess in an ideal world, we would actually want to measure this energy level picture, because in a sense, this electron image, although at a long range I can just represent it classically as an electron image charge, when we're closer to the surface, this is actually a much more complicated thing, in the sense that this potential has to sort of converge on the potential of the electron inside the bulk. So that is actually quite sensitive to the material, and these energy level splittings will be sensitive to that. So in an ideal world, we'd measure these energy levels as a function of surface separation. But of course, that requires you to actually hold the Rydberg atom at a given distance from the surface, and quite a close distance from the surface at that. So we haven't done that. Just as an aside, I mean, clearly, if the Rydberg energy levels are perturbed in this kind of way as you go towards a surface, then if you were thinking about resonant dipole-dipole interactions between two Rydberg atoms, then that's going to be affected by the distance that eventually the distance the molecule is from the surface. In fact, it's going to be affected both by an external field that might be applied. This shows you energy levels at different fields, as well as by the distance from the surface. When you go even closer to the surface, these energy levels start to cross over, as shown here, and the map becomes very complicated. If you look at the potential of the electron, here is the electron bound to the atom. Here it is in the metal. What happens as the molecule, this is for 40 AU from the surface, this is for 20. As the atom gets closer to the surface, the barrier gets narrower, and eventually the electron can tunnel out. And that gives rise to ionization. So this is what's illustrated here. You can see as you start to get some penetration to the surface, the Rydberg wave, if you like, goes into the surface. For metals, in general, the Rydberg electron is going to be degenerate with the conduction band of the metal. And it won't really make much difference what the metal is. However, if you take certain kinds of surface, for example, this shows you different kinds of the dispersion curves for different kinds of copper surface. And it's quite a complicated diagram, but the only thing I want you to get from this is that if you plot, these are just the low Rydberg states plotted, but you can see that if I take a copper 100 surface, that the Rydberg energy levels actually lie in a band gap between the valence band and the conduction band. And I'll come and talk about the effects of that later. Okay, so I'll be showing you, I've already shown you some of these wave packet calculations. These are performed by propagation of the time-dependent Schrödinger equation. The details of these calculations we reported in Phys Rev A this year. We use a discrete variable representation to do these calculations. We have to apply an absorbing potential to sort of to represent the ionization. And I'm happy to talk to people about them afterwards. So far, we've only done them for either for H atoms or xenon atoms. We haven't actually done them for the molecules that we've studied experimentally. So experimentally, this is how we do our experiments. Actually, we don't do it one molecule at a time. We have a beam of molecules which are excited by two lasers into a Rydberg state. They interact with a surface. They're ionized, and we apply a field to extract the ions, or in some cases, the electrons. You can see in this fancy diagram, the actual image charge appears here as the ion is formed. There it is. I've actually got someone in my group who makes pop videos in his spare time, so it's quite useful. But okay, this actually is very similar to the experiment that Barry Dunning did, and is currently doing as well with atomic Rydberg states. The point is that the ion will plummet into the surface unless we do something to pull it away. And the strength of the field required to pull it away reflects how close it is to the surface when it ionizes. So this is a little bit more of our experiment. There's a beam which seems to have disappeared here, but there's a beam of molecules comes along here. It's crossed by two laser beams. One's actually a VUV beam at 110 nanometers. The other one is a UV beam. These are what someone described as coming from 1980s pulse dye lasers. They then interact at grazing instants with the surface. If we form ions in the gas phase, they will take a different trajectory to those which are formed at the surface, so we can distinguish between them. And we've just built a new apparatus, which we're currently just starting to operate, which has, it's pictured here, and it has a wide range of kind of surface analysis techniques, LEAD, XPS, surface manipulator with heating and cooling, so we can really investigate different kinds of surfaces, ion gun for cleaning and so on. Okay, so with H2 Rydberg states, we excite in two steps, one VUV photon to this intermediate level, and then a UV photon to these Rydberg series up here. Because this is a molecule, we have to consider the vibration and rotation of the ion core, and this n plus quantum number, which is quite crucial in the results I'll show you, is representing the amount of rotation of this iron core. And what you can see is that from this level here, we can populate states with n plus is 0 and n plus is 2. In fact, principally, the states we see are actually n plus is 2. And these energy level spacings here are just the difference of the rotational energies of the H2 plus ion. So if you look at the spectrum, it looks like this. This is the n plus is 0 threshold, and this is the n plus is 2 threshold. And principally, we're going to be looking in this region here, where you can see these 17D, 18D, 19D, and 20D states. Actually, although they look like they belong to this series here, they don't. If you look at the comb here, they're actually belonging to this ND2 series. That is, they actually have 2 units of rotational angular momentum. And the n plus is 0 ones actually disappear around here because of predissociation. Okay, so this is the kind of way that we present our results typically. And this is a plot of the detected ions from this surface ionization versus the field that we apply. And first of all, what you can see, this is for different principal quantum numbers. And what you can see basically is we need to apply a larger field for n is 17 compared to n is 22. And that's not surprising because you'd expect n is 17 to ionize closer to the surface, and therefore it requires a larger field to pull the ions away. These profiles typically have 2 edges to them, an onset of detection and a field ionization cutoff. If we make the field too big, we just field ionize in the gas phase. And as Barry Dunning's group showed with their work on xenon, the minimum field that you require to extract the electron, the ions, depends on the kinetic energy of the molecules coming in and the distance of ionization. So an increasing field basically means a decreasing distance from the surface. And if you put some actual numbers on it, these are being ionized at about 100 nanometers from the surface. Here, this field corresponds to about 180 nanometers from the surface. So bigger principal quantum numbers means ionizing further from the surface. As I mentioned, the Rice group studied ionization of xenon atoms, Rydberg atoms, and are continuing to do some work in this area. And they observed similar kind of behavior here that for lower principal quantum numbers, you see signal at higher fields. However, when you actually put their data on top of ours, I literally did this by stretching the figure, so apologies for this, but you can see that for their n is 17, has a threshold of about 1,000 volts per centimeter, and our n is 17 has a threshold of about 500 volts per centimeter. So that means mysteriously that apparently these H2 Rydberg states are ionizing further from the surface than the xenon ones. And there is a slight difference in the angle of incidence, so it does affect the kinetic energy slightly, but that would actually make things even worse. So the explanation for this comes back to the fact that we're populating states which have a rotational angular momentum, and at some point in this process, that rotational angular momentum is getting converted into electronic energy, in effect, or the rotational energy is getting converted into electronic energy. And if you take a state here which has a principal quantum number n is 17, then it's almost degenerate with an n plus is 0 state with n is 23. And it turns out that when we populate a state, these states here, n is 17, 18, 19, they actually end up behaving as though they're in n is 23, 26, 29, or 33. And that's because the energy has been transferred from rotation into the electronic motion. And this is a little video that shows that here's a fast rotating H2 plus molecule. It's just exchanged energy. The electron has gone out into a higher orbit. And now it can ionize further from the surface. The proof of this actually comes from this, what looks like this very noisy structure here. This is completely reproducible, and these are actually resonances in these profiles. Now, it turns out that these are to do with energy level crossings in the Stark map. Here we're populating 17D, 18D, and so on, Rydberg states. There are actually a huge number of crossings, and these peaks actually correspond to many overlapping features. What we did to look at this a bit more clearly was to populate a variety of different levels in the Stark map and see what kind of profiles we got with those. So here's the actual spectrum. We can sit our laser on any one of these. What you can see is that actually every level has a different kind of profile, but every one with resonance effects, some of them even with like farnoline line shapes and things like this. So this is very intriguing, but really the proof that this has to do with level crossings comes if we actually generate the Stark map. So this is a bit of a complicated map, but what we're populating are these black levels here, n is 17, n plus is 2, which are almost overlapping these red levels, which are to do with n plus is 0. And every one of these black levels has a different set of crossings with the red levels, and that's why you get a different profile. And yeah, this is just a typical example of where we can literally look at the energy level crossings and line them up pretty directly with what we see in the spectrum. So what we're seeing here is actually a mapping out of these energy level crossings. What's actually happening is we're ramping our field up to a particular value. We're leaving the molecule there. It then interacts with the surface. And it's actually in that time between ramping up the field and interacting with the surface that this state has long enough to switch from one state to the other. These levels are very weakly coupled, so it actually takes a long time for that to happen. This is a kind of slightly curious experiment. One thing you'll see here is that if it turns out that actually the most important crossings are between this manifold here and this one here with our red ones. And you can see that this suggests a kind of onset of crossings that would look like that. When you actually look at the, we see the same behavior in the ionization profiles. So in actual fact, in this case, it is these level crossings which are really dictating what we see as much as anything. There are some subtleties in all this. It turns out that when the molecules go towards the surface, they will undergo additional Stark shifts of the levels. They will undergo additional crossings, which will depend on the applied fields. And that does actually affect their probability of ionization. And in actual fact, the relative intensities of these features appear to have some dependence on those kind of final crossings as it reaches the surface. So this is principally a gas phase process that's going on at these level crossings, but there are some additional effects which happen as the molecule comes close to the surface. Okay, so that's a very complicated story. And just to illustrate more of the complications, I pointed out that these profiles show these sort of Farno line shapes. This is actually due to coupling between levels at level crossings between metastable states, which are actually above the continuum for field ionization. And we get an interference between the if you like, the auto-ionization of that level and the direct ionization to that level. This is actually an example, those of you that are familiar with the Farno line shape, we normally think of it in a radiative process. This is actually an example of a non-radiative Farno profile, because it's actually happening from the level that we excite to via two non-radiative processes. Okay, now another thing we can do is actually detect electrons rather than ions. This was surprising to us, and okay, it was easy to do the experiment. We just reversed the field that we were applying to see whether we could detect electrons instead of ions. And there are a couple of ways that the electrons could be produced. One is that the ion core will be accelerated towards the surface, and it could knock out an electron via an Auger process, which we could detect. The second way is sort of illustrated by this wave packet calculation that for a certain wave packet, a part of the electron density just may go backwards as it reaches the surface. And if you look at the potentials in this reversed field case, it's kind of obvious that this can happen because if we apply the normal ion extraction field, the electron potential looks something like this blue dotted line here, and the electron can only go out one way. But if you apply the reversed field, the electron can either go towards the surface, as in with this pink barrier here, or towards the vacuum out this way. So the potential is lowered on both sides. And when we did the experiment, we found, this is just comparing electron profiles in blue with ion profiles in red, we found very similar looking profiles, but actually extending over a wider range of fields. And it turns out that this appears that the electron is just almost behaving like a classical particle in terms of where we're seeing the threshold for appearance of electrons. This is potentially actually quite useful if you want to detect low Rydberg states, because the fields that you need to detect the electrons in these experiments are very much lower than you would need to do by field ionization. So, and in fact, even an NS2 or 3 Rydberg state will ionize at a surface if it gets close enough. Another thing we've looked at is thin film effects, and we're trying to ask the question, well, if you have a film which is thinner than the Rydberg orbit, does it make any difference? Or if you make the film a bit thicker, what happens then? Here is a picture which shows, from a theoretical point of view, what some of the effects might be. Here you have a dielectric in front of a metal, and this is the potential, which has this strange, it's almost like a two-dimensional quantum well in front of the dielectric region. It's because this potential is trying to go down here, but the dielectric gets in the way and pushes it back up again before it can come down in the metal. So this may have some influence on the dynamics of the electron trying to tunnel into the metal. We did some calculations. These are just an example for NS3. And here you have a thin film case. Here's the thin film in yellow. You can see what happens here is that the Rydberg electron wave function is actually kind of going sideways into this two-dimensional well rather than tunneling straight into the metal as in a free metal case. So we did some experiments again with H2 molecules rather than H atoms. Here's a very complicated picture, the kind of thing we've done. So we've prepared, for example, surfaces with 6.5 nanometers of aluminum oxide aluminum oxide on aluminum, or 50 nanometers. We've done some with silicon dioxide on chromium, 100 nanometers, 200 nanometers. There are just two things to take away from this picture, which is quite complicated. The first is that in all cases, when we have a thin film, it's actually easier to extract the ions than when we don't have a thin film. That's probably partly to do with the shielding of the force, which is trying to pull the ion into the surface in the clean metal case. The other thing is that the very thinnest film, the 6.5 nanometer film, shows the biggest effect. And we don't fully understand that. Whether it has something to do with this quantum well state or not remains to be seen. But thinking about this quantum well state and the effect it has on the dynamics led us to just to think a little bit about, in general, how could electronic states, how does the sort of specific potential affect this process? So far we've I'm just going to present some results of some calculations. But as I was saying earlier, we've looked at these copper surfaces. Here's a copper 111 surface, which has a valence band, a band gap, and a conduction band. Here's a copper 100 surface, which has a valence band, and a conduction band that's actually above the vacuum level. And the Rydberg states, in this case, will kind of sit in the band gap. There are some surface states which are sitting there as well. These are actually image charge states which form Rydberg-like series of the surface itself. The interesting question is, if our Rydberg state is more or less degenerate with some state which is sitting in the band gap, then does this affect the process? So we've done some simulations of this. This is a complicated table, but this shows you the Rydberg energy levels for an H atom in EV. This shows you the energy states of a copper 111 and a copper 100 surface. And you can see that for certain n values, for n is 2 for example, this Rydberg energy lines up with a state, or a surface state here for the CU100. I've got 2 minutes, so I'll just show two more pictures here, then I'll be finished. So for n is 2, for example, if you run the simulations, you can see, this is for a free metal, copper 111, copper 100. You can see the copper 100 actually ionizes first, and that's because it's almost resonant with a state of the surface. The copper 111 ionizes last. If we go to n is 4, just to show a different example, here the energy is minus 0.85. This is almost degenerate in copper 111 with an image charge state, whereas it's degenerate with nothing in copper 100. And when we run the simulation, what you find is the earlier ionization, this time with the copper 111. You can see it here. But you can also see the Rydberg wave function spreading out sidewards into a two-dimensional surface state. So with these kind of simulations, this suggests that there are a range of very interesting effects due to the specific nature of the surface and electronic structure that can be probed in experiments potentially. And in fact, we've run these simulations up to n is 7 so far and seen similar effects. Okay, so in summary, that's kind of as far as we've got to in terms of our work. I think I've shown you some of the sort of rather rich complexity that you have to deal with when you have molecular Rydberg states interacting with a surface. And I think I've shown you that to some extent these types of experiments and theory can probe both the Rydberg state itself and the nature of the surface. And with that, thank you for your attention.
Okay, any questions? Yes. In both the simulations and the experiment, what is the role of the temperature of the surface? I mean, in the experimental chamber, you said you have a heater, so you can change the temperature. Did you do this?
Yeah, we haven't done that yet. I think that's going to be, that's quite high on my list to do, but we haven't.
Especially if you have a band gap, of course, this should be.
Yeah, I think that potentially is a very interesting experiment. So we can both heat and go down to liquid nitrogen temperature. So
currently, it's room temperature.
Yeah, currently it's room temperature. Yeah.
I think you were suggesting that for H2 near a metal surface, it could ionize like a micron away, or something like n equals 30 or something like that. Would that be right?
It was well for n is 20, it was about 200 nanometers.
And what's the scale roughly with n? Is there a scaling?
Yeah, so this will scale roughly with n squared. So yeah, by the time you've gone to n is 30, 40, then we are starting to get close to a micron. But going back to Ben's talk, I know Ben had to go, but yeah, he was kind of 50 microns from a surface at n is 40, and I would think it's you have to be down to a few microns before you feel the Stark effect of the image charge is really starting to have an effect on things. So it may well be. In a way, I'm not surprised that in what he was talking about, there wasn't a major effect of the surface, given he was never closer than 50 nanometers from the surface.
dielectric case, that's what interests Charles and me.
Yeah, of course.
Well, you've
got a whole new effect which is dominating, as you showed, these surface polaritons, which I think is yet another interesting effect really to explore in some detail. And I mean, yeah, I think we could quite easily put a quartz surface in, although I mean there are problems with surface charging and in really interpreting these sorts of experiments. And yeah, when you're applying fields to try and pull ions away, it's quite hard to do that experiment.
Yeah. To what extent is predissociation a concern for your experiment?
It is. I mean, the states that we used. I mean, the time scale of our experiment is about 10 microseconds. So that's the time between excitation and arrival at the surface. And the states that we've chosen were chosen because it's slightly longer than that, basically. But there are other states which we couldn't investigate because they just disappear on a on a time scale, possibly sub-nanosecond time scale. This is the problem with molecules, that sort of you'd think you could pick any Rydberg state, but of course you can't, because the number that which actually last long enough to do anything useful with it is quite small.
What's the energy distribution of your beam coming in?
Incoming beam. Well, it has a translational. It's a supersonic beam formed in a. So it has a translational temperature of around about 0.5 of a Kelvin in the center of mass frame of the moving molecular beam. So it has a relatively narrow distribution, but in kind of trying to understand our results, we obviously have to take that into account, because kinetic energy is one of the factors in the field that in calculating what fields you need to apply to pull the ions away.
So did you do experiment as a function of incoming velocity of the beam?
No, I mean in principle we can do that by seeding the gas in different in different mixtures, and we can also effectively change it by changing the angle of instance, which with our new experiment we're better set up to do. And of course we could even decelerate the beam, as was shown in next week.
Just on a related question, what's the best distance resolution you can achieve in where the ionization takes place?
You can nail it down pretty well to within a few percent, certainly. Somewhere I don't think I've got a figure there, but for example, I mean typically these for an atom you'd expect them to be ionizing at about 3.5 times the Bohr radius. And where the data does fit that kind of thing, then it fits very well. And if you change that to 3.4 or 3.3 times the Bohr radius, it doesn't fit. So one can really nail it certainly to a few percent this distance. But having said that, there is a certain probability as it comes in that it will ionize and it grows. The probability grows, so they're not all ionizing at exactly the same point. There will be a spread, but it does rise quite exponentially, and so it's a narrow distribution of distances.
Any other questions? Okay. Well, if not, I guess we should thank Tim again. I love the organizers. Want to say anything? Certainly should thank all the academics.
Only one left here. I don't have much to add except to thank everyone for coming. You did all the work. I wanted to thank Francis, but he's not here, so he left. But have a happy return. So see you hopefully next year, I think, in Dresden.
Let's thank our Lisa Bastille, our administrator.
Absolutely. Lisa, who's not also
not
here,
but
in the office.
She may be watching.
She's watching this. They're all watching this.
So, thanks everybody.